This photograph shows the Tigris River during its seasonal flood stage. The water volume swells and the river current accelerates into a heavy, violent force moving through the city. Below the surface, the water carries a destructive payload: thousands of tons of uprooted trees, agricultural runoff, and heavy urban plastics. Municipal water systems rely on intake stations built directly into these banks. The pumps have to ingest millions of gallons of water without ingesting the debris. When that debris hits the intake screens, it chokes the flow. The water pressure inside the intake drops instantly, a condition engineers call head loss. You have massive multi-million-dollar pumps demanding a constant feed of water, while tons of branches and plastic are slamming into the submerged grates, starving those pumps of that exact flow. The traditional response to this has been human labor. Facility managers send crews out onto the wet concrete over the floodwaters with long poles and manual rakes to physically pull the blockage free. Human muscles simply cannot outpace the physics of a flood. The current drives debris into the screens exponentially faster than a ground crew can clear it. Achieving continuous operation requires removing humans from the equation entirely. You have to build an automated, three-tier mechanical defense system. The first instinct in intake protection is to build a massive steel wall directly across the channel, perpendicular to the flow. This forces the structure to absorb the river's kinetic energy. The drag force acting against that flat surface mounts until the barrier simply snaps. To survive the current, the barrier tilts to a precise angle, between 20 and 45 degrees. Instead of fighting the kinetic energy of the water, this angle harnesses it. The current naturally pushes heavy, floating debris along the edge of the barrier, sliding it past the intake and sending it downstream. These floating debris booms are built to take a heavy beating. The surface floats are molded from high-density polyethylene, making them highly buoyant even when struck by whole tree trunks. Suspended underneath the floats is a rigid skirt that extends 30 to 60 centimeters deep to catch waterlogged timber riding just below the surface. But the plastic floats aren't taking the structural strain. A heavy steel tension chain runs through the center of the system, acting as the load-bearing spine that absorbs the pull of the river. A river like the Tigris introduces a massive environmental variable. The water level fluctuates wildly from week to week during the rainy season. To account for this, the boom's anchor points ride on vertical sliding poles. This level compensation system lets the entire barrier rise and fall with the river surge without ever losing tension. By managing the physical load through deflection, the boom ensures that massive structural threats never breach the intake. Only medium and fine debris make it to the internal channels. This technical schematic illustrates the second line of defense: a mechanical bar screen and automated trash rake, bolted directly into the flow path at a steep 75-degree incline. Here, you can see the precise kinematics of the system. A motorized chain drives a set of specialized horizontal teeth that comb directly upward through the stationary vertical bars, physically lifting the trapped debris out of the water. The immediate operational question is whether to leave this heavy machinery running continuously.
Running the rake 24 hours a day burns through electricity and wears down the drive chains prematurely. The efficient solution is to automate the system to run strictly on demand. Engineers install differential pressure sensors across the bar screen. When debris blinds the screen, downstream pressure drops. That drop triggers the system. The motors power on, the rake cycles until water levels equalize, and then shuts down. There's always a risk that the rake teeth catch on something immovable, like a heavy boulder wedged tightly between the bars. To prevent the motor from tearing the machinery apart, the drive mechanism relies on fluid couplings and shear pins. If the rake jams, these components intentionally slip or break, stopping the motion before catastrophic torque destroys the primary gears. This active removal mechanism creates a highly responsive, self-regulating barrier that defends the main pumps without requiring constant monitoring.
Down at the deepest stage of the intake sequence, completely submerged in the dark water, sit the fine V-wire passive screens. The threats at this depth are microscopic but dense. Thick, heavy river silt, dense, sticky algae, and fine submerged weeds pack into the narrow gaps. Mechanical rakes are useless here. The screens are too delicate for steel teeth, and the sheer depth makes routine manual scraping impossible. The solution requires a completely different physical mechanism: pneumatic backwash, driven by an air burst cleaning system. On the surface level, a massive rotary screw air compressor,
pulling up to 125 horsepower, feeds into a heavy-duty steel receiver tank. This tank stores a large volume of potential energy in the form of compressed air, holding it at a highly volatile 150 pounds per square inch. The release is controlled by a fast-acting pneumatic butterfly valve, designed to snap fully open in a fraction of a second. When triggered, that stored pressure rushes down the piping network and erupts outward from the inside of the submerged screen in a concentrated 3 to 5 second blast. The sudden volumetric expansion of the air creates a shockwave in the water. It physically severs the adhesive bonds of the mud and algae, blasting the biological mat outward where the river current sweeps it away. Pneumatic clearing restores full hydraulic capacity to the deepest screens in seconds, eliminating the need to send human dive teams into lethal flood currents. This cross-section diagram shows all 3 structural layers operating seamlessly during a severe flood. The boom handles the macrokinetic impact of whole trees, the mechanical rake manages medium structural threats, and the airburst system continuously clears microsediment from the deepest screens. For operators like the Nineveh Water Directorate, committing to this level of automation requires a high upfront capital cost. But that investment is measured against the hidden, compounding financial drain of a passive, manual setup. When a manual screen fails, a single rogue log can shred a turbine impeller. You then pay for the replacement hardware, the massive expense of unplanned municipal downtime, and the logistical nightmare of bringing in dredging equipment to clear the channel. Above all, you eliminate the severe occupational hazards of sending maintenance crews directly over deadly storm surges with hand tools. Integrating deflection, active raking, and pneumatic backwash is the required engineering baseline to secure a municipal water supply against the raw physics of a river.